speed of the light in the is universal constant, no matter who measures it. This is only true in the vacuum in free space. Vacuum, we can remove all the vacuum. And general relativity is nothing but Einstein general relativity is about gravitation, curved space-time, geodesics, black holes, wormholes, and other etc. things. Okay, that is the more concept will be included in the general relativity. This is the application. What is that? Differential geometry of general relativity. Of course, differential geometry is the language in which Albert Einstein general theory of relativity is expressed. According to the theory, universe is a smooth manifold. According to that theory of Einstein, our entire universe is a smooth manifold equipped with a pseudo-Riemannian metric, another type of metric which describes the curvature of the space-time. Okay, just imagine how that curvature will be formed. Why the earth is revolving around the sun and moon is revolving around the earth. That is because of this reason. Just look at that. This is the famous, I think you know, Einstein field equation. I need one more equation. Before that, put enter. Put enter. It will move to next slide. This slide not appear. Okay. Of course, that is you can leave it, no problem. That is the Einstein theory of relativity. Let's look at that. For your all that LHS side is geometry, differential geometry, and your LHS is nothing but your RHS is nothing but the physics. The entire theory of relativity can be defined in mathematical model, that is we can call it as a Einstein field equation. Of course, the universe is defined in terms of Einstein field equation. One side is physics, another side is exactly that Riemannian curvature. Look at it. This LHS will say, tells matter and energy how to curve space-time. It that will tells that the matter energy how to move through the curved space-time, how to move through the curved space-time. Einstein general theory explains the gravity. Newton view could not explain. Why do different masses fall at a same rate over a small same time? Because of this reason. Look at that, this video. That video is also not coming. Either is it display there only? All display ಆಗ್ತಾ ಇದೆಯಾ? Is not this one, this slide. Okay. This is, you can look at that. According to general theory, relativity, some important slides they are not showing. That is very interesting slides. General relativity, the space around the sun is curved. Space around the sun is curved. Look at that. And this curvature, the bending of the curve, that is the curvature, forces the earth. Clean observe madri, very interesting adu. Okay, apple falling idiyalla, adu story alla, that is reality. How that apple will fall. Okay, so if apple is fall in your head, why moon is not fall in our head? Isn't it? Because this is also there in there. So that is because of that reason. Look at that. That earth to revolve around the sun because of the forces of the curvature. Okay, this animation is best animation, just you can observe that. This is space-time curvature. Okay, differential geometry and relativity combinedly we studied with the help of the Einstein field equation. Next. But Einstein theory, that is Newton theory says that no, light and time, look at that, the space and time at a time bending, at a time, look at that, coordinates along with that. Okay, that is at a time bending. No, it is not Einstein theory. This is the Newton theory of that thing. This is exactly the difference. This is also space time, but in the different structure. Okay, for every, not only earth, not only sun, for every celestial elements can be controlled because of their space and time curvature effect. This is the best animation. Okay, visualization, you can see that. I'm skip this one. The light is bending. That text is not coming. The text, ಅಲ್ಲಿ text ಇದೆ, ಅದು ಡಿಸ್ಪ್ಲೇ ಬರ್ತಾ ಇಲ್ಲ. Yes, sir. These are very important, sir, for students. Okay. How the light is bending when the object will come. This is look at that. That is the galaxy, one galaxy. The light from the one, so any source that will bending immediately when we can reach us come to that part. Okay. Of course. This matrix are nothing but the, look at that kinds of matrix in physics. These are all the models for solutions for our Einstein field equation. Solutions, different types of matrix. I will show you that. These are black hole matrix, we can call it as black hole matrix. You know, you see that structure. Non-rotating and rotating black holes are also there. Uncharged and charged that black holes are there. But these black holes can be modified or modeled with the help of the different types of metrics. The name of that matrix, that is Schwarzschild metric, Reasoner metric, and etc. etc. How the black hole will be formed? This is also same thing. The first picture of the black hole is captured by Abel telescope in 1978. That is theoretical, not a practical one. But very recently in 2019 is the first illustrative black hole can be identified. Okay, in 2019 and 2019 also another structure they are entered, and 2021 very magnificently that they are looking the along with the magnetic waves. Okay, in the black hole there is a magnetic, one force is there, that force we can call it as a magnetic waves. That magnetic waves can also be visualized in 2020-21. That is the image of that one. Okay. White hole is also there. I think you heard only that black holes, but white hole is also, that is another structure. Galaxy from black hole, in between but two black holes and one white hole and black hole there is a wormhole. So that is our structure. Sorry. This is our model. Very recently published this paper, the mathematical model of a worm model by using this metric. Metric means one shape function we are using. Based on the data available by that shape function, what we can get the result that can be embedded into the three-dimensional picture. Okay, that is this model, that is a lower universe, upper universe, and mouth and tunnel of that between the two mouths. So that is the structure of another black hole. Look at that. That is the mathematical picture, geometrical observation. When we can visualize that structure by using that computer visualization, this is the wonderful structure. Same, that is mathematical, but this is visualization, real. Okay, so everything can be observed. Black holes means, I think, imagine the galaxies can be observed. The galaxies can be collapsed in that when we can enter into that black holes. Okay, so that much of force can be created in that black holes. That is the beauty of that understanding the universe. This is new animation that very recently taken this animations, visualizations. Okay, new black holes visualization. And how two black holes will be formed and collapsed, but they have to take its their own direction, because they are belongs to the same category, you know. They have not what is that observing each one. That is the interesting thing, this animation. Curvature, leave it. This is the I will, sir, 5 minutes I will finish this one. Okay, dear friends, the cosmology, you know, cosmology is the study of whole universe. There are two things are there. In Kannada ತುಂಬಾ ಕ್ಲಿಯರ್ ಆಗಿದೆ. ಒಂದು ಬ್ರಹ್ಮಾಂಡ ಅಂತ ಕರಿತೀವಿ, ಎರಡನೇದು ವಿಶ್ವ ಅಂತ ಕರಿತೀವಿ. ಐ ಥಿಂಕ್ ರಿಮೆಂಬರ್, ಬ್ರಹ್ಮಾಂಡ ಅನ್ನೋದನ್ನು ಕಾಸ್ಮಾಸ್ ಅಂತ ಕರಿತೀವಿ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಫಿಸಿಕ್ಸ್, ಆ್ಯಂಡ್ ವಿಶ್ವ ಅನ್ನೋದನ್ನು ಯೂನಿವರ್ಸ್ ಅಂತ ಕರಿತೀವಿ. ಯೂನಿವರ್ಸ್ ಈಸ್ ದ ಓನ್ಲಿ ದ ನೋನ್ ಥಿಂಗ್ ವಾಟ್ ವಿ ಹ್ಯಾವ್ ಸೀನ್ ಆರ್ ಅಬ್ಸರ್ವ್ಡ್ ಟಿಲ್ ಟುಡೇ. That is, we can call it as a universe. But the so many universes are there. That is, we can call it as a cosmos. The difference between, I think, a cosmos is too familiar illa namage, but you should know that cosmos is different and that universe is different. But interestingly, only one point I will stress you: the entire universe is defined mathematically by using only two simple words. Simple words. You believe it or not, just you can observe that. These are all different types of cosmology. I will, when the time is available, definitely I will think. The principle of cosmology is only two mathematical words. One is homogeneous and another one is isotropic. What a beautiful. ಅಲ್ವಾ? ನಮಗೆ ಗೊತ್ತಿರೋ ಎರಡು ವರ್ಡಲ್ಲಿ ಇಡೀ ಪ್ರಪಂಚನ ನಾವು ಡಿಫೈನ್ ಮಾಡ್ತೀವಿ. ಐ ಥಿಂಕ್ ಯು ಕ್ಯಾನ್ ಸಿ ದಟ್. ವೆರಿ ಸಿಂಪಲ್ ಮ್ಯಾಥಮೆಟಿಕಲ್ ಮೀನಿಂಗ್ ಅದು. ಹೋಮೋಜಿನಿಯಸ್ ಮೀನ್ಸ್ ಆಲ್ ಪ್ಲೇಸಸ್ ಆರ್ ಲುಕ್ಸ್ ಅಲೈಕ್. ನೀವು ಯಾವ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲ ಎಲ್ಲರೂ ನೋಡಿ, ಆಲ್ ಆರ್ ಲುಕ್ಸ್ ಅಲೈಕ್, ಬಟ್ ದೇರ್ ಇಸ್ ನೋ ಸ್ಪೆಷಲ್ ಲೊಕೇಶನ್ ಇನ್ ದ ಯೂನಿವರ್ಸ್. ದಟ್ ಈಸ್ ದ ಮೀನಿಂಗ್ ಆಫ್ ಹೋಮೋಜಿನಿಯಸ್. ಬಟ್ ಸೆಕೆಂಡ್ ಒನ್ ಈಸ್ ಐಸೋಟ್ರೋಪಿ. ಐಸೋಟ್ರೋಪಿ ಮೀನ್ಸ್ ಡೈರೆಕ್ಷನ್. ಆಲ್ ದ ಡೈರೆಕ್ಷನ್ಸ್ ಆರ್ ಲುಕ್ಸ್ ಅಲೈಕ್. ಪ್ರಪಂಚ ಯಾರು ಎಲ್ಲಿ ನಿಂತ್ಕೊಂಡು ನೋಡಿದ್ರು ಒಂದೇ ಕಾಣುತ್ತೆ, ಗೊತ್ತಲ್ಲ ನಿಮಗೆ ಅದು? ಲುಕ್ಸ್ ಅಲೈಕ್, ಬಟ್ ದೇರ್ ಇಸ್ ನೋ ಸ್ಪೆಷಲ್ ಡೈರೆಕ್ಷನ್ ಇನ್ ದ ಯೂನಿವರ್ಸ್. This is the definition or principle of the universe. So that is what we can cosmological principle. But there is a problem in that principle. What is that? These are the problems. Would it possible to that universe is? Because we don't know that how to define, how to measure the length. The first possibility is homogeneous but anisotropic, inhomogeneous but isotropic, and inhomogeneous and anisotropic. This is the present research is going on, how the universe is look like. Okay, this is difference between that cosmos and the universe. Okay, just one last. This is up to this we have to say that how that Big Bang theory, what is the theory of things will be formed. Look at that. From one light, that is earlier it is just a singularity, one point in this universe. When we can explode it, that will galaxies will be formed. That is Big Bang singularity. And the second one is first star formation in 15 to 150 billion years ago, right? And the solar system appear in 9 billions earlier. Okay, so that is what is that galaxy formation by Big Bang theory. That is very recently that Big Bang theory is introduced. Alan Guth is introduced that concept. Alan Guth in 1981. And okay, the shape of the universe, just we are imagining there are three shapes. One is our universe is just like a flat, and another one like a sphere, and another one like a, that is only the imagination, theoretical. Okay, so that is the structure. But will the universe expand ever? The universe is expanding. The present theory says that the universe is expanding every minutes of the in the time. That is why what happens next? Look at that. Is the universe collapse somewhere in time? Is the universe finite or the universe is infinite? Okay. So answer all the above question is important, but the final structure of the universe depending upon the two factor. One is the density of the galaxies, and second one is the rate of expansion. So this is the one, what is the end of the cosmos? Entire, this is one theory is proposed. That is three popular theories of the end of the cosmos are the big freeze, big rip, and big crunch. Okay, so the formation is also big bang, but the end is also some words big, either crunch or collapse. So this is what is that exactly the structure. How reap will be taken, how the freeze will be taken, and how the crunch will be happen. This is what is that the theory, how that this is big crunch, collapse. ಇದ್ದಕ್ಕಲ್ಲೇ ಹೋಗ್ಬಿಡ್ಬೋದು ಎಲ್ಲದು. That theory will be says that no one can knows. Okay, the stars will be collapsed each other and disappear and clash together. Each stars and each galaxies, the universe will be collapsed. Okay, these are, look at that, just it will become again singularity, right? So this is the one interesting information. These are all our recent papers we have published on this particular topic. We have started this research very recently from 2022. Still then we are working and published 22 papers on this relativity and cosmology applications. Thank you. Thank you very much for your patience listening.
So I request all the audience to interact with the resource person during the lunch time in person. So I thank you very much, Professor, for your excellent. It is not a video you have shown. It is really the most realistic pictures one should see, everyone, and one must understand. Kindly interact with the resource person. He will be available amidst us. Thank you.
Thank you, sir. And at the outset, I express my sincere thanks to that all organizers, particularly the Narari taking a lot of risk too for me, and Patil sir, and Madam and Boregowda. So thank you very much for the organizers. Thank you one and all.
Thank you, sir, for your valuable keynote address on cosmology and relativity. Now I thank Professor R. Rangarajan, sir, for chairing this session.
So now we will break for lunch. So all the resource person will be guided by our research scholar to the respective place. And students lunch is arranged near the stage in 2 counters. The delegates and the research scholar, their lunch is arranged in G31, ground floor, G31. And the students who have not collected the coupon, they can collect it from Miss Veena, who will be standing near the stage. So sharply we are going to assemble back here by 2:15. We are going to start our next session at 2:15.
3 concepts, if you are well aware of it, you know it, how to find a solution. Generally, when you are in UG or PG, only you study all the concepts. You do not know what exactly the applications are going to be there. You know only finding a solution. That's what a research scholar needs. If you know the solutions for a simple system, all the PG or UG courses, you can be a good research scholar. But the problem is, many students in UG and PG, you study only for getting pass. You never ever concentrate on learning things. That is the biggest problem. When you become a research scholar, there you will try to study once again. By then the time was already passed. Nobody will be there with you to explain when you go for a research. Being a research scholar, nobody will come to you and explain. There you get stuck because your studies are not well when you are in UG and PG. You study your courses well and thorough. Then when you become a research scholar, I don't think that there will be difficulty when you are doing research. Right. My problem is very simple. So Rayleigh-Bénard convection, understanding the heat transfer analysis, and understanding the instability analysis in the layer. So the physical configuration is going to be like this. Before that, my presentations involves the physical configuration of the problem, some introduction regarding to literature and mathematical formulation, and stationary and oscillatory convection. There are this stationary and oscillatory convection. Stationary convection is done for nonlinear convection, but oscillatory is not done. Oscillatory part only we started during 2015 and 14 and 15. And there are many works we have done on oscillatory convection, especially involving the nonlinearity and solution methodology and results and discussion. The figure will be like this. My model is very thin layer, very simple layer. You type Rayleigh-Benard convection in the internet, you will get a complete the scenario, the solution of this problem. Very thin layer. I said thin layers. So the bottom and the upper plate, two plates are there. This is extended infinitely extended, and I don't bother about the side walls because the length is infinite. So side walls are not going to be affect the instability of the layer. So the bottom layer is heated and the upper layer is cooled. So that means you see here the bottom layer, the delta T stands for the difference, the temperature difference between two plates. These are the Benard cells. When the temperature difference, the temperature gradient is large enough, there are two stabilizing factors. One is thermal conductivity and another one is viscosity. Thermal conductivity and viscosity are going to be two stabilized factors. Whenever this delta T overcome these two stabilized factors, then the fluid which is lying inside the plate try to move up. The simple example is when you are preparing a tea or when you are boiling a water, you can see that after some time the water is trying to heat up. Initially it is stable. When the plate gets energy, so then the fluid is trying to move up. That means the bottom one is hotter plate. When there is energy, when you are heating the bottom plate, the delta T, the temperature gradient will become more, which influences the thermal conductivity and viscosity. Then the fluid try to move up, and after certain while, until where it has energy, up to there it goes up. When it loses energy, it falls down. So going up, coming down, going up, coming down. That's why in the bowl you can see there are like what to call it as some streamlines, isotherms you have there. You can see in the bowl. So it goes up and comes down, goes up and comes down, so that from the bottom layer the heat transfers slowly to the upper. Now what does it means that? So there is a temperature, there is streamline flow. So there is interaction between temperature and streamline flow. So there is a non-linearity. So your brain and boy's brain, girl's brain interacted, non-linearity, here streamline flow, and the heat transfer interacting, non-linearity. Now the question is to understand the transfer analysis between the medium. So when there is interaction, it is very difficult to find a solution for it. For example, you see that there is a oil, thick viscous, there is a water. You can simplify easily, you can vary it. What happens, there is a milk, sugar and water. You mix up, you will get one kind of resultant. That means some tea or coffee, something like that. But whereas you cannot differentiate it. So they all together mixed becomes nonlinearity that can be only analyzed. So here also same thing. There are two factors. One is fluid flow, another one is energy transmission. There is interaction. That means there's a nonlinearity comes in. So the nonlinearity between energy and fluid flow, that has to be generalized and find how the heat transfer is taking place. And moreover, what about plate nature? What are the boundary conditions? Whenever you have a thin plate, you need to look after the boundary conditions. So by this you will get differential equations. Differential equations you get. Whenever you have a differential equations, you need to have either initial conditions or boundary conditions depending on the geometry of the problem. Now, how to analyze the heat transfer between the two plates and how to control the heat transfer between the two plates? That's the question is. how to simplify this non-linearity, how to generalize the steady of heat transfer between the two plates. And you can also, one more thing, add another one, concentration. Put some salt. Put some salt. It's going to be another one. You get another equation. So another non-linearity added. Another coupling between salt and streamlines or fluid flow. You put again nanofluids. Another model you will get it. So differently, it depends on you that how many concentrations, how many constraints that you wanted to add to the medium. So those many equations and that much of complications coming. So then again finding a solution is very difficult. So to control the heat transfer, or if you add concentration, control the mass transfer, what I am going to do is we apply some external forces, that is in terms of temperature modulation or gravity modulation. Now you see this, when the fluid moves off from the bottom plate to upper plate, due to the gravitational force which is acting to the downwards, so what happens is it pressurizes the fluid not to come up. So it goes up, energy over comes down. Why it is coming down? Because of the gravitational force. So the gravity acting against to the fluid motion. So if you hold the gravity, you can control the stability analysis, you can control the heat transfer or energy transfer in the medium. And also external force, you can apply even, yeah, this is a gravity modulation. Free, rigid. First two, there are many studies, free and free rigid boundaries. Lot of studies, numerous studies has done. But whereas when it comes to the matter of rigid free and rigid, see the first three are not much realistic, but people are working on those first three. But which is realistic is, the realistic is 3 and 4, of course, rigid in nature. But the concentration is, first two already we have done it, now the third and fourth I am trying to find a solution. Now temperature, the boundary conditions for temperature or isothermal, and oppositely lower plate and upper plate, we changed. How many boundary conditions are there? 4 into 4, 16 boundary conditions. Whereas you can see in many of the papers, they will see only 1 or 2 and then generalize the study. See, finding a solution for rigid boundary conditions, somewhat difficult, but whereas what we do is, we take free boundary conditions and then extend the model to the rigid boundary conditions. Right. Now, these are the different cases, various types of modulations that already have been done. We have also many papers on that. Next, same gravity modulation, temperature modulation. Now, what are the assumptions that we have in our model? The first one is, we have only 2-dimensional, that is x-axis and then z-axis. That's what it is, 2-dimensional. So why is my independent? So the roles are considered only in x and z direction. Now, Overbeck-Bosanoff approximation is considered, which means that the the density is varied with respect to only temperature. So the density terms are considered only in the time of buoyancy. That means gravity. Now we consider small scale convection, which means that the nonlinearity in the momentum equation, Q dot del, which is nonlinear term, because Q into Q product is there. That's why it is a nonlinear terms, which is very less, very small, because it will not affect, because we are concentrating on only energy. So the instability is the instability which is acting because of the temperature. That's why we are concentrating on temperature only, not the fluid motion or velocity. The last one is we consider only weakly nonlinear thermal instability. Weakly nonlinear I said. Nonlinear I said earlier, weakly nonlinear. To understand nonlinear and weak nonlinear is nothing but, at certain point of view when you are heating in the bowl, at a certain point of view the fluid tries to comes up. That point is going to be a critical state of a fluid. After that point, the fluid tries to comes up, the instability taking place. So near that point, we study the thermal instability. That means local nonlinearity near to the critical Rayleigh number. What about nonlinearity? Nonlinearity is beyond the critical state. So what happens it is, after 100 degrees Celsius, when you are heating the bottom, how the fluid motions will be, you can't control them. When the fluid is moving with stream functions, you can analyze. When the fluid is coming like this, ups and down, When you are boiling the water, what happens? Up to certain stage you can hold it, it's very hot. But after certain while, what happens? The fluid gets more energy and then perturbed. That's going to be very complicated to understand. That's where you are going for a non-linear thermal instability. That is actually a chaotic thermal instability. Right. Next, the model is, these are some old papers which are related to our model. So I don't explain, this is all very difficult to understand for you, right? Next. So these are the simple equations. Governing system of equations, mathematical expressions. See, mathematical expressions, if you know the solution methodology, you can easily find out a solution. That is the different. But physically in application only there is a problem to understand. Mathematically everybody can solve the system. But application oriented is the biggest problem. Right. You see that continuum equations, momentum, linear momentum equation and energy equation. So there is a fluid flow, that's why you need to consider linear momentum equation. There is a energy also, you need to consider energy equation. And continuum hypothesis delta Q dot equal to 0. That is the continuum hypothesis fluid, and fluid means it is moving from one point to one point. All the particles are adjacent to each other so that they are moving. So that there are streamlines. Continuum hypothesis, there is no breakage. If there is a breakage, which means that is a turbulent. You know the tap water. You put slow, the water comes along with the streamlines. You put faster, speed with force, there is a breakage. It is not going to be any more continuous. So all the fluid papers in the world, whichever paper it is maybe, whichever the work it might be related to fluid mechanics, the continuum hypothesis has to be satisfied. That's the logic there. But you see, according with this continuity equation, the system will be solved. You see here, my density Weber-Beck approximation, I said, rho, density is depending on temperature. And density is not a variable, it depends on temperature. As temperature varies, density value, it has some value based on the temperature. Now, how many equations are there? How many unknowns are there? Velocity, temperature, velocity, temperature, velocity, if you consider two variables, that means xz, u, w, two variables, temperature, three variables. How many boundary conditions you supposed to have? It depends, we will see later, right? Now you see this one, alpha T is the thermal expansion coefficient and Kt is the thermal diffusion. It is a thermal diffusion. After certain a while, the fluid try to move up. Diffusion means try to gets energized and then try to move up. That's thermal expansion or diffusion. Right, next. So that basic state, that means initial state. Initially means there is no velocity, there is no exchange of temperature. Initially means when there is no flow at all, when you are not heating, when you are not adding any temperature gradient to the system. Initial state, the velocity is 0 and P, pressure, temperature and rho are the functions of vertical direction, that is Z. So in that initial state, basic state, you can find a solution for pressure gradient and you can find a solution for density and you can also find a solution for basic state temperature or conduction state temperature. This is temperature, this for us ninth one is very important. When you consider gravity modulation, this is what you get. When you consider temperature modulation, you get a different solution. So this is actually gravity modulation, that is why it is linear. But these two, PB and rho B, these two basic states density and basic state pressure, they can be used when you go for a non-linearity, when you go for a solution when it's perturbed, right? So hold these equations, next. So now you perturb the system, that means after giving some energy to the system, the fluid becomes unstable. The unstable quantities, the disturbed quantities are added to the velocity, density, pressure and temperature, where dash denotes the perturbed quantity. So additional quantity, that means unstable quantities. Now scaling factors, you see this one, the non-dimensionalization with respect to Kt, that is thermal conductivity. So why do we do with the non-dimensionalization with thermal conductivity? Why can't with viscosity or dynamic viscosity? Because the study entirely depends on only temperature. The study entirely depends on only temperature. That's why you do non-dimensionalization with KT. Of course, you can also use viscosity, dynamic viscosity, you get the same resolution, but only the forms are different. Since we are concentrating on temperature, we do non-dimensionalization with respect to KT. Then, why do you do non-dimensionalization? Why do you want to do non-dimensionalization? Because in differential equations or in system of equations, there are different units for pressure, velocity and other things. When you do non-dimensionalization, the system of equations are going to be independent of dimensions and becomes, you get some parameters. The non-dimensional system of equations, you are going to get a different form. There you get a non-dimensionalization numbers. Now you see that one, stream function, U and W, the velocity components can be replaced by only one variable, that is in terms of xi. So that is what U and W are replaced by dou psi by dou z, dou psi by dou x. And these are the stream functions satisfies the equation of continuity, first equation. So accordingly, we use this one and convert or reduce the number of variables in the system. Why do you do non-dimensionalized with respect to thermal conductivity? Why not others? The velocity is expressed in terms of stream function to reduce the number of variables. Then what about next equation? This is system you are going to get. Yes sir, conclusion. It goes fast, remaining all figures only. So these are the systems, 13 and 14. You see, one is momentum equation, the second one is energy equation. Where is the nonlinearity comes in? The nonlinearity comes in Jacobian. This is simpler Jacobian. This interaction between, coupling between fluid flow and temperature. Coupling between fluid flow and temperature. See, when you don't have this one, it is a linear model. When you don't have this one, it is a linear model. Solution is like simple eigenvalue problem. Now you see, where is the modulation system? This is Rayleigh number and sitting here gravity modulation. This is energy equation. This term is sitting in temperature modulation. So you can analyze both the gravity modulation and temperature modulation by sample of these two equations. Now you see this. Next, the solution methodology, the boundary conditions. The boundary conditions, first one, stress-free boundary condition. Psi and second derivative psi is equal to 0 at the lower plate and upper plate. Stress-free means there is no surface tension acts on the plates. There is no surface tensions. I told you that it is smooth layers, smooth and thin layers. So stress-free boundary conditions and rigid boundary condition, you see, there is no smoothness. Rigid means the fluid does not slip easily. That's not going to be smooth. Rigid means the fluid stick on to the boundary. Stick on to the boundary, then the solution methodology is very difficult. Next, this is first two are velocity profile. Second one is second two are isothermal boundary conditions and adiabatic boundary conditions. Isothermal, heat exchange to the surroundings. Adiabatic, heat does not exchange to the surroundings, only to the boundary itself. Now, so gravity modulation, temperature modulation. You see that in the gravity modulation, temperature is, basic state temperature is in non-dimensionless form, it is 1 minus z. But in temperature modulation, when the gravity vertically modulated, this is the form. When the plates are modulated, this is the form that we consider for temperature. Now, the solution methodology. Of course, you see this in normal mode analysis, the psi and temperature can be expressed in the form where you see right hand side equation 23, sigma t is sitting there. Sigma t is sitting there. When sigma is 0, you see it's a marginal stability. When sigma is in terms of complex term, it is not marginally, it is oscillatory. So sigma is 0. Many papers have been developed for nonlinear case, but when sigma is non-zero, which is oscillatory, no paper has been done. Of course, papers have done, the work has done for only linear theory, but non-linear theory. That non-linear part we have contributed, you can see. So we have taken sigma is oscillatory, that means imaginary terms, and then developed oscillatory convection for nonlinear theories. Next, the solution methodology, the regular expansion, the Rayleigh number and the stream function and T or regular expansion, the perturbation method here it is lower system. I told you that initially Ax is equal to 0. How to find a solution Ax equal to 0 homogeneous system? That is the only this one eigenvalue problem. Now find a solution for psi 1 T1, where psi 1 T1 you find a solution applying the boundary conditions, you get some solutions. Earlier it was where A and B are the amplitudes of the convection. So they are related with B is equal to A. Where A is I1 is equal to some integrating with respect to temperature modulation. This is classical Rayleigh-Bénard number, Rayleigh number. Next, this is for the rigid boundary cases, rigid boundary conditions. Earlier it was free boundary condition. Rigid boundary conditions, this actually FZ stands for some Chandrasekhar number which is truncated and find a solution for mu. There it is given. So now finding a solution for rigid boundary conditions actually takes huge calculations. So we have used some mathematics and then found a solution. Now this is Chandrasekhar number and it has been found some the approximate value for mu 1 is equal to this one by using truncation error methods. Next, conclusion. So similarly you go for a second order solution and find heat transfer coefficient Nusselt number equation 35, and even third order solution we don't find, we find the existent solution using solubility condition. We get the one equation. That's what I asked you, the Bernoulli equation, solution to the Bernoulli equation. It is like that only. Equation 40 is derivative dou A by dou T A into A to the power of 3 y cube. So it's a Bernoulli equation and you need to solve this equation, but it's not like our simpler ordinary differential equation. It has so many time dependent coefficients. That's a problem. But in our studies, we find direct solution. But in the research, when it comes to the matter of research, many number of coefficients will be involved in the equation with the time coefficients. There you need a lot of stress to find a solution. Now the solution cases, these are the numerical studies. Of course, you can also do analytical studies when there is no any modulation term. Now you see this one, heat transfer analysis with respect to the time, because the boundaries are varied in sinusoidal manner. That's why the results are in sinusoidal manner. You see, whatever the problem you take, but the solutions should match with your expectations. You expect some results after completion of your work that has to match, or else the studies are going to be useless. Right. This one is mean Nusselt number, same results but differently. And this one is the effect of amplitude of modulation. When you enhance the amplitude, you see the difference between, in particular interval, there is a variation in particular interval. In that particular interval, there is enhancement in the transport energy. And similarly, this one is frequency of modulation. The system actually reduces the energy transmission, and different kinds of, 3 types of temperature modulations: lower plate modulation, upper plate modulation, and only lower plate modulation, different kinds. And also this one is, this is Nusselt numbers with respect to the frequency of modulation. Whenever the frequency goes goes further, it is reduced, the heat transfer is reduced there. Now you see this one. This is very important. The first paper that we got in 2014, International Journal of Nonlinear Mechanics. For this figure only that paper is accepted. We have compared the results for free boundaries, rigid boundaries and free boundaries. When the surfaces are rigid, it's not very so easy that the plate gets energy very faster. That's the difference. Next. So modulated system, unmodulated system, especially for gravity modulation. When there is a gravity modulation, so there is no, there is a sinusoidal manner effect. Unmodulated system, there is no modulation effect that can be observed. And the streamlines. Next, you can see isotherms. Initially, isotherms are like a flat. As time goes off, isotherms moves upside down faster. That's where you can see the temperature transfer is taking place. Or this or some conclusion I told already. Now some references, related references. This is Ambedkar Central University from Lucknow. When I was doing my PhD, 2014, Professor B.S. Baduria, left side, and PGS was there during my PhD. Actually, initially, we have invited him for international conference, and Saravanan sir, and these are my seniors, all the folks sitting there, seniors, my seniors. Of course, I finished my PhD in 1.5 years and submitted 2 years. That's because of some delays. Right. Thank you.
Thank you, Kiran sir. Because of time constraints, Kiran sir has not gone in detail. Anyhow, Kiran sir is here tomorrow also. Those doing especially research scholars and MSc students, you can interact with him if you have any questions in your mind. Thank you, sir, for your wonderful talk regarding dependent and independent variables, how you relate to the day-to-day life with friends. Thank you on behalf of our department and university.
I'm requesting Professor Patil sir to give the moment of on account of vote of thanks, and I would like to thank Palakiran sir to giving his precious time for us and giving inspirational talk for our students. Thank you, sir. Now, our next speaker is Ramanesh sir.
Hello, so good afternoon once again. Now next talk is given by Professor H.S. Ramanesh sir, Professor and Chairman, Department of Mathematics, Karnataka University, Dharwad. He sir is a very good friend of us. Oftenly we are visiting to Karnataka University, Dharwad, and our Dharwad faculty members also visiting to our department every on exam related all work. Now I am very happy to introduce Professor Ramanesh sir. He's completed his postgraduate and PhD degree from Karnataka University, Dharwad, and his research area is on mainly graph theory. In particular, spectral graph theory, energy of graph theory, chemical graph theory, distance in graphs and topological indices. Professor visited foreign countries, Indonesia, China, Taiwan, and delivered and invited talks, and has a collaborative work with the foreign researchers. Professor has more than 150 publications, and under his supervision 13 students already got the PhD degree. Sir, we are fortunate you come over here from Dharwad to here to deliver a lecture. Our research scholars and MSc students and UG students got benefit for your talk. Thank you.
Hello. I'm audible? Okay. First of all, let me thank the organizer for inviting me for this conference, and thank to Patil Mallikarjun for his kind words about me. My topic is somber energy of a graph. First of all, what is meant by energy of a graph? A graph is a collection of points and edges. Okay. So if there is a edge between 2 points, we can say those two points are adjacent. So here we model the molecule. Okay, basically this talk is related to the chemistry. A chemical molecule which contains the hydrogen and carbon atoms. So here we represent that molecule in terms of graph. So carbon atoms are taken as a points or vertices. Okay. And if there is a carbon bond, means bond between the two carbon atoms, we'll put the H. So this molecule is converted into the graph model. Hydrogen atoms are ignored because hydrogen atoms has no much impact on the whatever the results we are obtaining for the corresponding molecule. Then this graph is converted into the matrix. Okay, adjacency matrix. So matrix is indexed with the vertices, and the entries of the matrix is 1 if there is a edge between the point Vi to Vj, that is ijth entry, otherwise it is 0. So molecule is converted into the graph, graph is converted into the matrix. Now using the linear technique, linear algebra techniques, that is properties of the matrices, and using the eigenvalues, we can study the physical properties of the corresponding molecule. So you need not to go to the lab and do all the experiments. Okay, so this is the advantage of converting any physical problem into the mathematical model, and then using any mathematical technique which you know, or you need to develop some technique to solve that model, and you can study the properties of the corresponding physical problem. Okay, so this is the applied mathematics. So mathematics is there. When you apply it, it becomes the applied. Okay, so you need to develop techniques, or you need to use the available technique to solve the physical problem. So here also same thing. Okay, but I am not going to do detail in chemistry. I will do the mathematical properties of the corresponding concept. Okay, so graph is converted into the molecule is converted into the graph model. Graph is converted into the matrix. Then using the matrix techniques, we can learn the basic properties of the corresponding molecule. So it is a simple graph here. Okay, simple graph means it has no multiple lines, it has no loops. Okay, the vertex set is denoted by V of G with the vertices say V1, V2, Vn, and the edge set is E1, E2, Em. So the order of a graph is n, that is number of points, and the size of a graph is m, that is a number of lines in a graph. So degree of a vertex is nothing but the number of lines incident to that point, and if the degree of each point is same, say it is equal to r, then we can say the graph is regular graph of degree r. Okay. So corresponding to the adjacency matrix, as I already told, the adjacency matrix of a graph is a square matrix of order n, where n is the number of points. Okay, and the ijth entry Aij is 1 if there is a edge between Vi and Vj, otherwise 0. Okay, so diagonal elements also 0 here. Okay, because there is no loop. We are considering only the simple graphs. Okay, no lines, means no multiple lines and no loops. Then as you know, the characteristic polynomial of a graph is nothing but the characteristic polynomial of this matrix. Okay, it is denoted by phi g lambda, that is determinant of lambda I minus a of g, where I is the identity matrix of order n. And the eigenvalues of this matrix, usually denoted here lambda 1, lambda 2, lambda n, they are called the eigenvalues of a graph G, and their collection is called the spectrum of a G. Okay, and the energy of a graph G is defined as sum of the absolute values of the eigenvalues of a graph. Okay, now in the molecule, what I told, the molecule is converted into graph and then graph to this matrix. The eigenvalues are nothing but here energy levels of a molecule. When the electron transfer from one orbit to other orbit, they generate the energy. So those energies represented means approximately they will be the nothing but the eigenvalues of the corresponding molecular graph. Okay, and the sum of the absolute values of the eigenvalue is the energy of a graph, and it has a good correlation with the total pi electron energy of a molecule. So total pi electron energy of a molecule is nothing but the sum of the energy levels of that molecule. Okay, so you know the Schrodinger wave equation. Okay, so Haeckel, what he has done, Schrodinger wave equation he has transferred because it has a energy factor. Okay, so Schrodinger wave equation is transformed to the secular equation as a determinant of lambda I minus a. Okay, basically this adjacency matrix 1 and 0, but in chemistry, if there is a carbon-carbon bond, we'll put beta. Okay, that is this one constant in the chemistry. And if there is no carbon-carbon bond, we'll put 0. And diagonal elements are alpha. Okay, so and alpha and beta are the empirical constants. So that matrix, that is called the Huckel matrix, that can be written as alpha I plus beta A. Okay, alpha into I is the identity matrix, plus beta into adjacency matrix. Okay, so at the ground state level, okay, at the ground state level where alpha is 0 and beta is 1. So when alpha is 0, beta is 1, that Huckel matrix is nothing but the adjacency matrix A, adjacency matrix of the corresponding graph. So there, since Huckel matrix is written as a alpha I plus beta A, you know the eigenvalues of a unit matrix, identity matrix. What is the eigenvalues of unit matrix? All ones. Okay, eigenvalues of a identity matrix are all ones. Eigenvalues of A are lambda 1, lambda 2, lambda n. Okay, so since Huckel matrix is alpha I plus beta A, you can get the energy levels, that is the eigenvalues of Huckel matrix, epsilon I you can say, is alpha plus beta into lambda I. Because eigenvalues of I are 1, 1, 1. Eigenvalues of A are lambda 1, lambda 2, lambda n. Alpha, beta are the empirical constants. So you will get the energy levels as alpha into 1 plus beta into lambda 1 or lambda I. Okay. So total pi electron is the summation of those energy levels. That is alpha plus beta into lambda I. Okay. At ground state level, I told alpha is 0 and beta is 1. So you will get the summation of lambda is. Okay. So this graph energy has a direct correlation with the total pi electron energy of a molecule. But I am dealing here, giving the lecture on the somber energy, not the adjacency energy. Okay. This is the adjacency energy. Starting the people have worked on this. Somber energy, so many other matrices introduced in by the many researchers. Laplacian matrix is there, signless Laplacian matrix is there, distance matrix is there, Seidel matrix is there. Seidel is coming for the switching. It works with the electrical network. When you switch the button, the flow will not stop. Okay, you have to put in your switch in such a way that if you turn up, even the flow remains same. Okay, so that is a Seidel matching, that is Seidel switching matching, matrix. Okay, so many matrices are defined. Recently, the somber matrix is defined. So first of all, somber index. It is defined as summation of square root of di square plus dj square for every adjacent pair vi vj. For every adjacent pair, you have to take the sum of the square root of di square plus dj square. Di is nothing but the degree of the corresponding vertex vi. Okay. So square root of di square plus dj square is a Euclidean distance of a point di dj from the origin in the two-dimensional figure. Okay. You know the distance formula. Distance between the 2 points x1, y1 and x2, y2 is what? Square root of x2 minus x1 square plus y2 minus y1 square. So this is the distance between the origin 0, okay, O, that is 0, 0, and the point di dj. Okay. So it has a geometric meaning here. Okay. So square root of di square by dj square is the Euclidean distance. Okay. So it is taken as summation of all those distances. Okay. So here di is the degree of a corresponding point, and you have to take the summation over the only adjacent points. Okay, not all pairs, only adjacent points. So that is called the somber index. Okay, this is also one of the topological index. So topology indices, many are there, more than 150 so far. Okay, starting from the Zagreb index. Okay, Zagreb index is summation of di plus dj. Okay, sum of the degree of vertex vi plus degree of vertex vj, where vi and vj are adjacent. Okay. So this topology is why it is introduced to study the properties of the physical properties or chemical properties or physico-chemical properties of the corresponding molecule. To study those, the indices are introduced, and corresponding to those indices, the properties are studied. So recently, the Gutmann introduced the somber matrix as a square matrix of order n whose ij identity Sij is square root of di square plus dj square if the vertex vi is adjacent to the vertex vj, otherwise 0. Same as the adjacency matrix. In the adjacency matrix, we are taking 1 instead of 1. Here it is taken as square root of di square plus dj square. Okay. So as usual, the characteristic polynomial of this somber matrix is called a somber characteristic polynomial, and the eigenvalues denoted by rho 1, rho 2, rho n, and analogous to the ordinary energy, the somber energy is defined as the summation of the absolute values of the eigenvalues of this matrix. Okay, so that is called the somber energy. Why this name has come Sombar? It's the name of the place. Okay, it is the name of the place. Even Zagreb index. Zagreb is the name of the place, city in the Serbia. Okay, the group of people who are working in that place, that's why they are given this name, Sombar energy, Sombar index. Okay, Sombar index. Then energy is also obtained, so the name is given Sombar energy. Okay, it's the name of the place in the Serbia. Okay, see this graph having the 4 points V1, V2, V3 and V4, and the Sombar matrix is written there. Okay, from V1 to V2 there is a edge. Okay, so square root of degree of V1 is 1, degree of V2 is 3. So 1 square plus 3 square. Okay, that is square root of 10. So the entry V1, V2 is root 10. Whereas between V1 and V3 there is no edge. Okay, so entry corresponding to V1, V3 is 0, entry corresponding to V1, V4 is also 0. So like that, other entries are introduced. It is a symmetric matrix. It is a symmetric matrix. So since symmetric matrix, the eigenvalues are only real numbers. You will not get the complex numbers. Okay, because of the symmetry. And diagonal elements are 0. So for particular to this graph, the eigenvalues, that is the eigenvalues of the Sombar matrix are 7.2528, 0.7529, minus 2.828 and minus 5.177. Since diagonal entries are 0, trace of a matrix is nothing but the sum of the elements of the diagonal elements. Okay, so trace of this matrix is 0. So naturally the sum of the eigenvalues of such matrix is always 0 because of trace of a matrix. Trace of a matrix is 0. Okay, and the Sombar energy of this particular graph is 16.0114. Just you have to take the absolute values, sum of the absolute values of these eigenvalues. Okay, so sum of the bounds here, if G is any graph with n points and m lines and P be the absolute value of the determinant of this Sombar matrix, then the Sombar energy always greater than or equal to square root of 2 into f of G plus n into n minus 1 P to the power 2 by n. F of G is defined as summation of di square plus dj square. This is called a forgotten index. The name is given forgotten index. Why it is given the forgotten index? Because this index was introduced in the year 1978 to study some pi electron energy in that paper 1978. After 1978 till recent, nobody has looked to that. Recently people have started to study this index. So that's why the name is given forgotten index. Okay, from 1978 to recently means around maybe 2 years back, 2-3 years back. Okay, nobody has concentrated on that particular index. Okay, so recently the people who have studied that, they are given the name forgotten index because between that gap, nobody has studied. And you can wonder that there are many good results are coming on this index. Okay, it has more applicability in the chemistry, this index. I'll just outline the proof, how the result is proved in this. See, Sombar energy is summation of mod of rho I. Okay, square it. Squaring will get, this battery is not, squaring will get summation of rho I square plus summation of mod of rho I into mod of rho j. Okay, we know that the geometric mean of the set of numbers is always lesser than the arithmetic mean. Arithmetic mean is always greater than or equal to the geometric mean of the those set. Okay, so using that simple concept. Okay, so this side, left side, it is a geometric mean of